This video is brought to you by Squarespace. Hi guys, welcome to Amateur Chemistry. So we all know that there are a lot of dangerous substances all around us, ranging from highly flammable solvents to fatal poisons accessible by just mixing some cleaning supplies. Now, while all these things are indeed quite nasty, if handled properly, they aren't really that difficult to safely work with. Honestly, this is an argument that can be made for pretty much everything, no matter how toxic or flammable it is, but there are certain things that even when handled correctly are just a nightmare. Over my whole 2 years on YouTube, I've made a bunch of dangerous chemicals that are definitely no fun to be around, however none of them is nearly as bad as what I have planned for this video. You see, the thing that I am going to be making today is not only extremely toxic, but it's also a strong mutagen, straight up giving you cancer, can easily eat through almost anything and makes otherwise inert things go up in flames. This mystery chemical is something called chromium trioxide, and I recently got really intrigued by it and wanted to see if it lives up to all the horrors I read about it while researching for this video. Apart from testing my safety gear, I also plan to use this evil substance to do a lot of cool experiments, one of which will be turning some vodka into vinegar, which is the last thing you would expect something so dangerous to be able to do. To make this deadly cousin of the Philosopher's Stone, I will have to use another nasty and interesting compound which looks like powdered carrot and comes from some acid marinated forks. I've made it in a previous video and this one is sort of a sequel. Originally I wanted it to be just about making some chromium trioxide, but it turns out that this forbidden Cheeto dust made from forks has way more uses than just giving people cancer. It can be used to perform a whole array of really colorful and incredibly unique chemistry, so after diving deep into the chromium rabbit hole, I decided to try out all this wonderful stuff for myself. However, first I really want to tell you about this video's sponsor, Squarespace. Squarespace is an advanced all-in-one website creation platform for entrepreneurs to stand out and succeed online. Using it, you can easily create beautiful websites whether you're just starting out or managing a growing brand, and use them to promote your business or sell anything. Squarespace gives you access to amazing features like their new design intelligence that combines 2 decades of industry-leading expertise with cutting-edge AI technology to unlock your strongest creative potential and make your website personalized to your specific needs, which in my opinion is pretty damn cool. Additionally, Squarespace offers a wide range of useful tools like their email campaigns that are everything you need to engage your subscribers and drive sales, which combined with Squarespace's option for creating and selling your own online courses can expand your business like never before. For a free trial, check out squarespace.com, and when you're ready to launch, go to squarespace.com/amateurchemistry to save 10% off your first purchase. Anyway, before going full chemistry wizard mode, I feel that I should explain what will even be going on here, since such a big amount of chemical shenanigans can overwhelm quite easily. Okay, so the premise of this whole multi-episode project is exploring the chemistry of a quite overlooked element, chromium. At first glance, it looks like just another boring metal calmly sitting on the periodic table, but as I've recently come to know, it's far from that. Just by itself, it's already kind of unique, being the 3rd hardest element and having a beautiful luster. Chromium is also really corrosion resistant and forms the basis of materials like stainless steel. That's why it's often used to make things like forks, and while all this already makes it quite cool, it's still nothing compared to the properties of its compounds. You see, you can dissolve chromium in things like acids, making it into so-called salts, and this is where things get colorful, literally. The first thing that catches the eye when it comes to chromium salts is the absurd amount of colors they can display. This property is also the reason for the name chromium, since the Greek word chroma it's named after means color. Now, the color of a chromium salt not only depends on what other elements is the salt composed of, but also on chromium's so-called oxidation state. This is basically just a fancy term for how much chemical energy does the chromium atom invest in bonding to other atoms, and by manipulating it one can drastically change how chromium behaves. Take chromium in its third oxidation state, for example. In solution it has this lovely emerald green color and is generally quite safe to handle. It's even suspected of being an essential trace nutrient. Now, if we make it into its sixth oxidation state, it suddenly changes color to yellow and instead of being relatively harmless, can beat up your DNA, mutating it and giving you cancer. As I already said, it's not only the oxidation state that dictates how chromium compounds behave, because if I take my yellow chromium 6 solution and add a drop of acid, it becomes orange, and if I continue adding acid, it turns red. This nicely illustrates how dangerous chromium's oxidation states are, since this red stuff can easily vaporize some chicken. Now, my chromium trioxide is a red powder, which can give you an idea of just how chemically angry it is, and making something like this at first may seem kind of crazy. To be honest, it pretty much is, but I want to showcase this whole colorful process and have an unexplained urge to turn vodka into vinegar using forks, so I guess I can begin making some powdered death. For that, I got my whole 40 grams of fork-derived Cheeto dust, or more technically speaking, potassium dichromate, which already contains chromium in the right oxidation state, but needs to be a little modified to become chromium trioxide. I first need to strip it from the unnecessary potassium, and for that I first have to make it into a solution. To make this solution on the scale I want, I am going to need 100 grams of potassium dichromate, which is quite a lot more than what I extracted from the forks, and since I also want to use my homemade stuff for some other experiments, I decided to use only half of it and substitute the rest with some store-bought potassium dichromate. I conveniently have a good bit of it in this very old and suspiciously unlabeled jar, which I randomly found while cleaning my lab one day, and it's kind of scary to think that years ago when I started doing chemistry, I put jars with deadly chemicals in the most random places. Anyway, I combined 80 grams of the industrial potassium dichromate with my stuff for a total of 100 grams, and then got the beaker onto a hot plate. Since I have to dissolve this funky powder in water, I also threw in a magnetic stir bar to speed things along, and when everything was ready, I poured in 200 ml of distilled water. With some mild heating and stirring, everything dissolved rather quickly, and after adding some more distilled water for good measure, I was now left with some nice and mutagenic orange juice. Now, to rip off the potassium from potassium dichromate and simultaneously transform it into something called chromic acid, I have to acidify this juice. This can in theory be done with most strong acids, but in practice only concentrated sulfuric acid works, since it is both extremely strong and can hold on to a bunch of water, which will be vital later in the process. I have to use a good bit of it, or in other words 200 ml, which really seems like a ginormous waste of such a precious chemical, but here I don't really have any other option. I started adding it into my potassium dichromate solution really slowly because it has a tendency to heat up a lot when touching water, and since the whole solution is already warm, adding it too fast could result in the mixture boiling over and giving me one hell of a cleanup. Also, in this shot you can see me use a full 400 ml beaker of sulfuric acid, and that is because while making the chromic acid requires quote-unquote only 200 ml, the next step needs the exact same offering. In terms of the reaction going on here, sulfuric acid attacks the potassium dichromate, turning it into chromic acid and potassium bisulfate. The solution also changes color to dark red, rightfully indicating that it's even more dangerous now, and I have to be really careful to not get any on my skin. Anyway, with this scary chromic acid solution ready, I can now turn it into chromium trioxide, and this, as you might have already figured out, can be done by adding in another metric fricton of sulfuric acid. Before doing that, however, I decided to cool this beaker down a little since it's nearly boiling already and the next acid addition would turn it into an active volcano. I got it into this old pan which I then filled with a bunch of cold water, and after letting the temperature even out, I was now ready to make my cancer powder. I started slowly adding another 200 ml of sulfuric acid, and at first only the color changed to nearly black, meaning that this was still just some chromic acid being created. The sulfuric acid addition, as expected, warmed the solution up quite a lot, so after again letting it cool down, I poured in the rest of the acid, and this time some red precipitate started to appear. This finally was my chromium trioxide, which made this whole thing look like tomato sauce. In terms of what's going on here, the newly created chromic acid gets ripped apart by sulfuric acid, which really likes to steal water molecules of things, and in this case results in the formation of chromium trioxide. Now, I already have quite a bit of my product, but I can drastically improve the yield by cooling this solution down to make more of it crystallize out, and for that I put it into my fridge. When I came back a few hours later, the solution now looked much thicker, and a lot of those beautiful sparkly crystals managed to appear. In theory, I could cool this thing down even further to get more of my product, but then it would be much dirtier since there is still a ton of potassium bisulfate in the solution, and cooling it down more or adding less water at the beginning would cause a bunch of it to crystallize out and ruin the purity of my product. Anyway, to retrieve it from this beaker, the only real option is vacuum filtration, since this ultra-corrosive sludge can easily eat through things like cotton. Fortunately, because of the large crystal size of the chromium trioxide, it all filtered out quite quickly. Now, even though it looks quite dry, there is still a ton of sulfuric acid soaked into it, and since sulfuric acid can't just evaporate away, I have to wash the trioxide with something more volatile to later be able to dry it. This creates a bit of a problem, since pretty much every common solvent reacts with chromium trioxide. This means that I can only use a strong and at the same time volatile acid that will keep the chromium trioxide as a solid and be able to evaporate. Now, by far the best one to use for this would be hydrochloric acid, but it also reacts with chromium trioxide, so the only somewhat accessible one I can use is nitric acid. Now, nitric acid is always kind of a pain to work with and make, since you can't just buy it. Fortunately, I've already made it a bunch of times from various things, but the problem with that is that I left my whole supply in a different lab, and without nitric acid I didn't have anything to wash the chromium trioxide with. Since I didn't want to abandon this project halfway, I decided to whip up some nitric acid on the go, and since in this lab I currently don't have much equipment, I had to improvise a little. After scouring this place for anything useful, I managed to assemble this very amateur chemistry distillation apparatus featuring a comically long condenser and a rusty hot plate supported by some aluminum muffins. All this random junk was fortunately able to distill a mixture of potassium nitrate and sulfuric acid to obtain a good bit of some apple juice looking nitric acid with a concentration of around 70%. It's fortunately enough to wash my chromium trioxide, and it's quite funny to think that to even wash something as nasty as chromium trioxide, you have to use one of the nastiest acids. Anyway, after washing my product a few times, I left it to dry on the pump for a while, and when it got to a consistency of tomato concentrate, I got it all onto a petri dish. Apart from it, I was also left with a whole bunch of this black liquor collected from the filtration, which mainly consists of sulfuric and chromic acids and is closer to the potion of instant harming than anything I've ever made before. I actually want to keep it, since such an aggressive acid solution is capable of dissolving pretty much everything, including the most stubborn tars. I like to think of it as a last resort, good old method of cleaning glassware, and to store it I of course poured it all into a this time labeled and Teflon tape sealed jar, which is just poetic. Anyway, I now have to dry my chromium trioxide, and even though the nitric acid should evaporate quite easily, it is still really corrosive, so it would be quite unwise to just dry everything in the open. That's why I put the chromium trioxide loaded oven inside a fume hood so that all the deadly vapors will be just vented outside, and this contraption, apart from literally dissolving the insides of my oven, seemed to work quite well. After a few hours of heating, I was left with some nice and reasonably dry product, which looked like some fancy sugar. When I weighed it, it turned out that I managed to make 88 grams, which corresponds to a yield of 130%, which in turn means that I screwed something up big time. I of course didn't materialize extra 20 grams of product out of thin air, and this otherworldly yield means that my product either contains some impurities or is still very wet. The latter is probably the case, and this chromium trioxide still probably has a bunch of sulfuric acid stuck to it, which I didn't manage to wash away previously, and I definitely won't be making more nitric acid and repeating the deadly washing step because I gotta have some respect for myself. The presence of sulfuric acid also isn't going to be a big problem in any experiments I plan to use my product for, so I quit bothering about its purity and probably as a way of coping with this whole situation got it into a third jar of this project. Now that I finally made some weirdly delicious looking cancer powder, it's time to do some cool chemistry with it, and for the first experiment I wanted to show its reaction with water. I wanted to compare my chromium trioxide to some store-bought stuff, which instead of a red powder takes the form of those purple flakes, and upon combining them both with some distilled water, they quickly dissolved, forming a bunch of pure chromic acid. Chromium trioxide, much like sulfuric acid, really loves to steal water from everything, and even when left sitting in air, over time gets all wet. Another interesting property of chromium trioxide is that it melts when heated to just 200 degrees Celsius, which is really unusual for oxides in general. When molten, it also starts to quickly decompose to chromium-free oxide, which is much safer to handle, being this lovely green powder. It still amazes me that when chromium is bound to 3 oxygen atoms at once, it's so angry and unstable, but if you bind 2 chromium atoms to these same 3 oxygens, they become a nearly harmless green powder, often used as a pigment. It's a perfect example of just how random chemistry can be, and speaking of random chemistry, here is the reaction of chromium trioxide with some alcohol. As you can see, combining the two generates a big fireball and is the reason why washing chromium trioxide with alcohol is the dumbest idea ever. Anyway, now that I've showcased just how dangerous and deadly chromium-6 compounds can be, it's time to take a small break from playing with fire and instead focus on a slightly safer, albeit even more beautiful side of chromium, which is its incredible crystal growing potential. You see, you could in theory grow crystals of a chromium-6 salt like potassium dichromate, but there is a gigantic amount of reasons not to do this. Fortunately, there are still the more tame and just as beautiful chromium-free salts that, as it turns out, make some hella cool crystals. Now, to make a chromium-free salt, there are several ways, like the one I showed at the beginning, which involves just dissolving some chromium metal in acid, but it's far from perfect, and I want my crystals to be another reincarnated form of forks. This means that I have to turn my potassium dichromate into a chromium-free salt, and this can quite easily be done with the right kind of chemical energy. To start making my fork-derived crystals, I again have to prepare a solution of potassium dichromate, however this time on a smaller scale, and to begin I weighed out 49 grams of the beautifully orange dichromate powder. Now, I again didn't have enough of my own, so I used just 10 grams and substituted the rest with some store-bought potassium dichromate. Then, to dissolve everything, I used roughly 200 ml of distilled water and some light stirring. When most of the powder dissolved, I added in 30 ml of concentrated sulfuric acid, which much like before, turns some of the potassium dichromate into chromic acid, but this time it's not the chromic acid I am after, and the solution just needs to be very acidic for the next reaction. Speaking of it, to reduce this acidified chromium-6 solution to chromium-free, I have to use something called a reducing agent, and the cheapest and easiest one to use is ethanol. Now, it's the exact same thing that a few minutes earlier burst into flames in contact with chromium-6, but here its reaction should be much calmer and achieve a more desired effect. I started slowly adding 31 ml of some 96% ethanol dropwise, since the reaction it causes produces a gigantic amount of heat, and much like before, I really don't want it to get out of hand. Now, in terms of what adding some Everclear to an evil orange juice actually does, it's quite complicated, and to not bore you with the details, you can think of it as the acidified chromium was extra angry and wanted to beat anything suitable to death, or in a more chemical term, oxidize it. it. This oxidation causes the chromium 6 to calm down a little, which means getting reduced to its third oxidation state. Now the ethanol, upon taking such a severe beating, becomes sour, in other words turning into acetic acid. This reaction is really similar to the one that turns vodka into vinegar I am so enthusiastically talking about. However, it generates the acetic acid as an unwanted byproduct, and in the next video I will have to really tweak it to get some real yield. Also, because of the generated acetic acid, my whole lab now smells like vinegar, even despite me working in a good fume hood, which is like a cherry on top of a cancerous cake. Anyway, the ethanol addition went on for quite a while because the reaction constantly boiled, and each time I squirted in a drop of ethanol, I was afraid it would pull a prank on me. Fortunately it didn't, and after about half an hour of adding ethanol, I was left with this nice green solution. Now, the chromium-free salt generated by this process is something called chromium potassium sulfate, or chrome alum for short. It's actually the exact thing I want, so in theory I can now leave this solution and wait for some nice crystals to appear. I got it into my fridge to try forcing the crystals out, but after a whole night of cooling, nothing seems to happen. After all this, I was left with some thick green mess, and I had to do something to summon the crystals. I thought that if I boiled this solution down a little more and then cool it again, something would happen, but as I've already experienced several times, the crystals just didn't want to show up. Now, I had another trick up my sleeve, which is something I would do even if I had gotten some nice alum crystals, and that is diluting their color with a different alum. You see, the crystals of pure chrome alum are purple and so dark they seem black, so to make the purple color more apparent, you have to somehow dilute them. For that, you need to find a colorless crystalline material with the same molecular structure as chrome alum so that it can integrate into it, and for this, the best thing to use is something called potassium alum. It has the exact same structure as the chrome one, but has an aluminum atom in the center and is colorless, making it perfect for this job. I've actually already made quite a bit of it from wood and aluminum foil in a previous video, and it's really nice that I get to work with it again. Now, to dilute my chrome alum with it, I just need to dissolve some of it in the green solution, and to do that I first got the whole solution into a bigger beaker, diluted it a little and warmed it back up. I then started slowly adding in scoops of potassium alum, and when I felt that the chrome alum was sufficiently diluted, I got the beaker off the hot plate and poured the hot alum solution into 2 crystallizing dishes. I then left them overnight to slowly cool down, and in the morning drained the solution from the top, revealing some nice crystals. I was really happy that I finally got the alum to crystallize, but upon looking closer at the crystals, they weren't quite what I originally imagined them to be. You see, normal crystals of alums have flat sides and grow like these little pyramids. The chrome alum should also be purple, so when I looked at my very irregular and green crystals, I was quite dumbfounded. I didn't know if I just invented some new alum or majorly screw up, but these crystals were way too cool to throw out, so I kept them. Now, originally this was the point where I wanted to end this video, but after leaving the crystals undisturbed for like 2 months before starting to write the script for this video, I wanted to take one final look at them. You can imagine my confusion when the green crystals I made a while back for some reason turned purple and even more beautiful. They looked just badass, with this unusual structure really adding to their charm in comparison to some regular chrome alum crystals which I also managed to grow in the meantime. They didn't even seem to be made from the same chemicals. Anyway, if I want to enjoy those crystals in ways other than just looking at them, I have to get them out of the crystallizing dishes, and this is where things get real tricky. You see, they are really hard and seem to somehow be glued to their dishes, and to recover the other crystals I had to sacrifice the beaker they were in. I didn't want to waste even more glassware, so I decided to dissolve some of the crystals away to loosen them up and try scraping them out. To do that, I got this small crystal dish and poured in some hot distilled water, which dissolved them so fast I didn't really have time to get any big crystals out. I still had the big dish with a huge slab of crystals, and I poured the green alum water from the previous one into it, expecting the dissolution process to be at least a little slower. In the end, however, the dissolution speed didn't matter at all, since the dish randomly decided to just snap in half. It is quite ironic that I did this whole careful dissolution step to avoid breaking any glassware and broke some anyway. Fortunately, this didn't leave me with nothing, since with the dish snapped in half, I could now recover the partially dissolved crystal slab. I was really surprised that this whole gigantic project turned out like this, with all my months-long struggles leading to the creation of this epic cookie. Now, to preserve it for a long time, I couldn't just dry it out and leave it on a shelf, because chrome alum has this weird property of turning into chalk when left in the air for too long, so to extend the best before date of my crystal cookie, I need to laminate it with something. The most popular thing used for this kind of stuff is nail polish, but since I couldn't find any, I just got my good old acrylic car lacquer, which I proceeded to apply a few times onto the cookie. After leaving it to dry for a few days, I now had one of my greatest accidental creations, and making this cookie is the perfect end to this beautiful project. So far, I've really enjoyed working with chromium and its various oxidation states. All this wonderful chemistry can really make someone appreciate such a seemingly useless element. In the future, I plan to explore the world of chromium even further and turn some vodka into vinegar. Anyway, on a more personal note, my channel is now officially 2 years old and recently passed 50,000 subscribers, for which I am more than thankful to all of you. To celebrate, I plan to record a special similar in style to the previous one, but because of the colossal amount of channel related work ahead of me, I will probably get around to it in about 2 months. Anyway, for now, I have to thank you all for watching this really colorful project. If you enjoyed it, you can like this video, share it with a friend and subscribe to my channel. If you want to further support my work and gain access to exclusive content unsuitable for YouTube, as well as having your name displayed at the end of every video, I invite you to join my Patreon. Also, as always, a gigantic thank you goes to all my wonderful Patreon members for their support, which allows me to take on all these projects, and see you guys in the next video.